Hi, next we discuss about another problem using windowing method. Just read this problem. Okay, here the frequency response is given, that is e raised to minus 3j omega within the range pi by 3 to pi and 0 otherwise. And we want to find the filter coefficient h of n using Hamming window, and the length of the filter is given as n is equal to 7. Okay, this is the question. We want to design the filter coefficient. Okay, so the first step is that we want to check whether it is a linear filter or zero phase filter. Okay, from the frequency response itself, it is clear that this is a linear phase filter. What is the reason? Here e raised to minus 3j omega. There is a phase time, minus 3 omega is there. So it is a linear phase filter. Next step is that we want to decide which type of filter. It is a low pass filter, high pass filter, or any other filter. Okay, when we check the frequency response, first we plot the frequency response. It is clear that we have non-zero value within the range pi by 3 to pi. The same thing in the negative side also. Okay, so which type of filter is this one? From the frequency response, it is clear that it is a high pass filter. When we check this frequency response, it is clear that it is a high pass filter. Why? We check this positive half. Just consider this positive half from 0 to pi. Okay, we know that HD of e raised to j omega, it is periodic with period 2 pi. So from minus pi to pi, 2 pi. Okay, we consider one period. Within that, we consider this positive half. Here, it is clear that we will pass all the frequencies greater than pi by 3. We will pass all the signal with frequencies greater than pi by 3. So, it is a high pass filter. So, we decide the filter. It is a high pass filter. Next on the center of symmetry. It is a linear phase filter. So, the center of symmetry alpha is equal to n minus 1 by 2. N is 7. So, the center of symmetry is 3. With respect to 3, we get the symmetric response. Okay. So, here we check the high pass filter. So, what about other filter? We already studied about low pass filter in the previous problem. Here we discuss about high pass filter. Then what about the remaining filter? That means the band pass filter and band stop filter. Okay, here this frequency response, it represent the, what is one? It is a band pass filter. This one represent, it is a band pass filter. This represent band pass filter. What is the reason? When we check the frequency response, check this one from 0 to pi, positive half. The same thing here. When what is the why we check this positive half? We have the mirror image in the negative half also. So we check the positive half. From the positive half, it is clear that the frequencies, the signal with frequencies pi by 4 to 3 pi by 4. The filter will pass the signal with frequencies pi by 4 to 3 pi by 4. So it is a band pass filter. So what about band stop filter? Band stop filter, here also we can say that the ranges will be pi by 4. Okay, any frequency range pi by 4 to, I just here for an example I take this one. Here the signal with frequency range pi by 4 to 3 pi by 4, it will resist or stop the frequencies from pi by 4 to 3 pi by 4. So it is a band stop filter. Okay, we already discussed about all the filters: low pass filter, high pass filter, low pass filter in the previous problem, then high pass filter in this problem, and then this is the band pass filter and band stop filter. Okay, next we can move back to the problem. Here we check the what is the type of filter and what is that HD of e raised to j omega. Then from that we want to compute HD of n. Okay, HD of e raised to j omega, we want to compute HD of n using inverse Fourier transform. Okay, you can compute HD of n. The steps are mentioned here. You can check it. Okay, so you will get HD of n as like this. This is the expression, HD of n. Okay, so HD of n, we can say that HD of n is symmetric with respect to the point 3. Okay, index value 3 with respect to 3, the HD of n is symmetric. So the range of the values, index values is from 0 to 6. Okay, the center of symmetry is 3 and the length of the filter is 7. So the index n varies from, for HD of n varies from 0 to 6. 0 to 6. Okay, for HD of n. Then, and here it is a symmetric. So we can say that the 3 is the center of symmetry. So the value at 0 and 6 are same. HD of 0 and HD of 6 are same. And 1 and 5 are same. And 2 and 4 are same. Okay, you can substitute n in this equation. You can substitute n this equation. You will get HD of, when we substitute n is equal to 3, what happened? It becomes 0 by 0 form. So you can use L'Hospital rule, or the limit theta tends to 0 sine theta by theta equal to 1. That's discussed in the previous problem. You can cross check with that one. Okay, you will get the value of HD of 3. Then you get all these values. The values are mentioned here. You will get HD of 1, HD of 2, like that, up to HD of 6. Then next step is we want to check the window function. Here the window function is a Hamming window. We know its expression. This is the expression of Hamming window. Here in a window, it is symmetric with respect to 0. Okay, this expression represents a window function that is symmetric with respect to 0. So we have HD of n, the length of the HD of n is 7. We take 7 samples, same number of samples will be taken in the window also. But the ranges will be from -3 to 3, because the window is symmetric with respect to 0. So we need 7 samples. So we take the samples from -3 to 3. So total 7 samples. Then here also window also symmetric one. So W of 1 equal to W of -1, W of 2 is equal to W of -2, like that. W of 3 is equal to W of -3. Okay, substitute the value of n in this expression. You will get the window functions, sorry, window values. Then here HD of n is mentioned. It is a causal signal. That means have the values, non-zero values on the positive half. Then we compute the we compute the window coefficient. This is the window coefficient, but it is a non-causal signal. Here the origin, this is the origin, this is the origin. At the origin we have the magnitude 1. Here in HD of n at the origin the magnitude is 0. So it is a causal signal. The values on the positive half only. But when we compute W of n, the ranges will be from -3 to 3. Index values from -3 to 3. So we have the non-zero values on the negative half. So it is a non-causal signal. So we want to convert it into causal signal, because HD of n is causal and the starting is at the origin. But here the starting index is -3. We want to convert it into 0. That is origin. So we want to make it causal. For that we shift this W of n by 3 samples. So you will get an answer like this one. Just shifting the 3 samples right, you will get W of n. Then we multiply W of n with HD of n based on the index, same index value. Okay, we multiply, you will get H of n. This is the filter coefficient, have length 7. Okay, this is the filter coefficient, have length 7, and we find that it is a symmetric with respect to 3. We can check this is the index value 0, 1, 2, 3, 4, 5, 6. So total 7 samples will be there. So length of the filter is 7, and with respect to 3, it is symmetric. You can cross check. These are same, this one same, and these all are same. Okay, you can compute H of n.